Good morning. Welcome at the keynote session of Dr. Rogelj, who is Director of Research and Reader in Science, in Climate Science and Policy at the Grantham Institute at Imperial College London, and a Senior Research Scholar at the International Institute for Applied Systems Analysis. He explores how societies can transform towards more sustainable futures, connected Earth system sciences to the studies of societal change and policy. He has published on the effectiveness of international climate agreements, such as the Paris Agreement, carbon budgets, net zero emission targets, 1.5-degree emission pathways, and the interaction between climate and sustainable development. Joeri Rogelj has contributed to several climate change assessments over the past decade. He is a long-serving lead author on the annual emission gap reports by the United Nations Environment Programme, and he also contributed to the 5th assessment report of the IPCC, served as a coordinating lead author on the IPCC special report on 1.5 degrees of global warming, and as a lead author on the IPCC 6th assessment report. In the year 2019, he was the youngest member serving on the UN Secretary General's Climate Science Advisory Board. Joeri, please, the cloud is yours.
Thank you very much, and thank you very much for the very kind introduction. It's really a pleasure to be here with you today, and it's really nice to have this opportunity to do this in this hybrid fashion. Today, I will not be talking about my research, but I will be talking about the work that we did under the banner of the IPCC 6th assessment report. So let me get my presentation going. And I hope that by now you can already see my first slide. So indeed, what I will want to try over the next 45 minutes is kind of to give a very broad overview of the key insights of the latest IPCC assessment. And as you might know, the IPCC consists of different working groups that cover different aspects of climate change. This is, here I will be presenting the assessment of Working Group 1, which focuses on the physical science of climate change. Now, I want to start with a look back at one day in August when we woke up to these newspaper headlines in the morning. I apologize that the headlines that I'm showing here are quite UK focused, but that's the ones I was able to collect. But you can see here stories in The Guardian: global climate crisis, inevitable, unprecedented and irreversible. The Financial Times mentioning world likely to be 1.5 degrees warmer by 2040. Code Red for Humanity on many front pages, and that was because the UN Secretary General used that in its statement. So all these front pages of newspapers all around the world, and there were really news stories about this report in virtually every country in the world, are due to this report. And this is the Working Group 1 contribution to the 6th assessment report of the Intergovernmental Panel on Climate Change. And it was the day before that the summary for policymakers, this document that summarizes the hundreds and thousands of pages of the report for policymakers, was approved by delegates in the first ever virtual session of the IPCC. Now, I'm presenting this report today, but it is clear that this report was not written by me alone. Actually, I want to start this presentation by highlighting the really wide group of authors that contributed to this. Here you can see a picture of the core author team, actually, during one of our lead author meetings when that was before the lockdowns started. So this was in Vancouver. And what you can see here is the coordinating and as well as the lead authors of the Working Group 1 report. These are even not all the authors. There's also hundreds of contributing authors that provide invaluable input to the different chapters with their expertise. And then there's even thousands of reviewers that will go through the documents and make sure that they are scientifically robust. And I hope and I assume that probably some of you are also today sitting in the room or listening in. So without all those contributions, this report would not be what it is and would not be so impactful. However, the authors are only one part of what the IPCC constitutes. The other and very important part of the IPCC is shown here in this picture. The IPCC is ultimately an intergovernmental organization founded in 1988, and it has 190 member countries. And here in this picture, you can see the delegates of those 190 member countries sitting. This was during a meeting in 2014, but sitting in a meeting and going sentence by sentence over the summary of the report to approve it. Now, the IPCC is tasked to assess our best available knowledge about climate change and has to do this in an open, inclusive, and transparent way. And just to give you a flavor of what this process implies, it is basically a co-design process where governments and scientists work together to ultimately provide a document that is as robust as possible scientifically, but also as useful as possible for policymakers. And here you can see kind of a timeline, or not a timeline, but a trajectory that is followed from the start, where governments decide on IPCC products, for example, how many reports will be written, which reports, over the scoping process, where experts and governments decide what the exact content will be of the various reports, to the publication of the report. And important here to notice is that everywhere where I marked a step in blue, so from the beginning, over the selection of the authors, the review session, the review and the approval of the different drafts, all the blue steps are steps where governments provide input and where there's interaction with governments. This really highlights that this is a really integrated process, and that really also explains that why these reports are so impactful. Not only do they provide our best available assessment of the climate science, but they also provide a product that is co-designed, co-developed with governments, and where governments thus are which governments later on are eager to use. A last slide of introduction on the report, what went really into it. So we had an author team of more than 230 authors from 65 countries, about a third women and the rest men. 30% of those authors were totally new to the IPCC. 2/3 were actually newly took up leading roles, and that's important. We want this not to be, or the IPCC doesn't want this to be kind of an exclusive club of a few people, but it is really valuable to have this turnover of people with always fresh eyes and fresh perspectives. The review process of the report is extremely exhaustive. We reviewed in total 14,000 scientific publications, or assessed those as part of the work that went into this report. During the different review rounds, we received 78,000 review comments, and we need to respond to them, to each of those comments, in writing, one by one. And all those responses will also be published afterwards online. And finally, we had 46 countries that ultimately also commented on the final government distribution, which is the very latest draft before it is being approved. So, with all this context and introduction, I hope that by now, if this simple cover of this report already has a bit of a different meaning about all the work and all the effort and process that goes into preparing such a report. So what I want to do now over the course of the remainder of this presentation is really look at some of the key findings. And I will always start with one of the key messages that came out of the report, and then we would like to look at the underlying evidence that supports those key messages. The first message, key message that was plastered all over the media was recent changes in the climate are widespread, rapid, intensifying, and unprecedented in thousands of years. So that is a very strong statement. Let's see what the underlying evidence was that the report provides to support this. The first piece of evidence is that human influence has warmed the climate at a rate that is really unprecedented in at least 2,000 years. It's shown here in this figure, and many of the figures that I'm drawing from here in this presentation are from the summary, but I'm also drawing a bit on figures from the individual chapters where I wanted to highlight a bit more of the detail. And what you can see here is kind of a depiction of the famous hockey stick figure that has been part of the IPCC reports for a very long time. And what this basically shows is reconstructed historical temperatures for the last 2,000 years, and then observed temperatures for the last 2 centuries, roughly. And what you can simply see already visually from this figure is how the change in warming in the last 2 centuries is really unprecedented compared to what we have experienced and what our societies have experienced over the last 2,000 years. But the global warming is not the only dimension in which we can say that the human influence on the climate is really unprecedented. Another dimension that we can look at is the perturbation of biogeochemical cycles. This is just a blanket word for saying the CO2 concentrations, the methane concentrations, or the nitrous oxide concentrations in the atmosphere. And well, here you see two panels. The top panel shows atmospheric CO2 concentrations, and the bottom panel shows the growth rate of those concentrations. And what you can see in the top panel is that current atmospheric concentrations in the atmosphere are unprecedented for, and the report says, for the last 2 million years. So what we have here on the right-hand side, this is the current period. Here, the panel on the left of it is for the last 2,000 years. Then we look 800,000 years back with data from ice cores, and then we look even 60 million years back with data from sediment cores. And So based on this data, we can now say that the current level of concentrations of CO2 concentrations in the atmosphere is unprecedented in the last 2 million years. As you can see, there have even been periods in the very deep past when there were no human societies around where CO2 concentrations were higher. But even there, if we then look at the CO2 growth rate, so how fast we are changing our environment, also there we see that what is happening now is fundamentally different from what has happened over the past 60 million years. Here you can see the growth rate, and these small insets, they show the actual growth rate over different time horizons. This is for the last 200 years, this is for the last 100,000 years, and the left one here is for 10 to 40 million years before present. What is important to note here is that the units are different. The panel on the right shows changes in parts per million per year. This panel shows parts per million per century, and the panel on the left shows parts per million per 10,000 years. So it clearly shows that what we are experiencing today is several orders of magnitude faster than what we have experienced over the last 60 million years. And we don't have only evidence for CO2 concentrations. The same type of evidence is available for other greenhouse gases. Here, the top panel, this is only until 800,000 years because we only have that data from ice cores. Shows CO2 concentrations, methane concentrations, and N2O concentrations, nitrous oxide concentrations. And also here on the right-hand side, you can again see the growth rates. The gray ones are those over the last 800,000 years. The blue ones are those over the last century, roughly. The bars have the same height, but the units again are different. Here we have parts per billion per year, and here parts per billion per 10,000 years, or per 1,000 years, sorry. Again, showing that what we are experiencing today, also in methane and N2O changes, is several orders of magnitude faster than what we have experienced over the last 800,000 years. And that includes several glacial and interglacial cycles. Going on to the next high-level statement, it is indisputable that human activities are causing this change, making extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and severe. So the evidence that I showed before, the fact that it warms and that CO2 concentrations and methane concentrations are increasing, doesn't yet make the link with the fact, or with the cause of this increase. Doesn't tell us yet who is actually responsible or which process is responsible for the changes that we can measure and that we can observe. So here we have a different set of evidence that tells us, or that tells us unequivocally that human activities play a dominant role in the growth of atmospheric CO2 concentrations. And there are 4 lines of evidence that I want to highlight here, and each panel supports 1 or 2 of them. The first line of evidence is here in the left-hand panel. There, what that panel shows is just over time the actual atmospheric measurements of CO2 concentrations. And you can see that these are gradually increasing from 1960 to 2020. The small wiggles are the interannual variabilities, because there is more forest in the northern hemisphere than there is in the southern hemisphere. So winter or summer in the northern hemisphere changes global CO2 concentration slightly, but you can see that there is still a clearly upward trend. And the pink line here shows the difference between 2 measurements between the northern and the southern hemisphere, with higher CO2 concentrations be available in the northern hemisphere. And because most of the fossil fuel combustion in industrial regions is situated in the northern hemisphere, this is a first kind of fingerprint that we understand the source of this CO2 increase. The other lines of evidence are, however, even more compelling. The second and the third line of evidence is shown here in this panel on the right, where you can see kind of the decrease in carbon-14 and the ratio of carbon-13 to carbon-12. And what you can see is that both of those are decreasing. The decrease in the radioactive carbon-14 tells us that the carbon that is added to the atmosphere is very old, because it's depleted in all of the radioactive isotopes that were originally in there. And that's a clear indication that it is coming from fossil fuels. Another example or another line of evidence that it is coming from fossil fuels is the decrease in the ratio of carbon-13, which is depleted also in fossil fuels, because fossil fuels were originally plants, and plants preferentially take up carbon-12. So from both these lines of evidence, we know that the CO2 that is added to the atmosphere comes from a originally biological source, but which has been stored for a very, very long time, so fossil fuels. And the last piece of evidence is here the ratio of oxygen to nitrogen in the atmosphere, which is also declining, not drastically, but measurably, and with a rate that exactly explains the amount of oxygen that would be required to combust all the carbon that is required to add the CO2. Again, showing that the CO2 that is added to the atmosphere is the result of a combustion process. So with these four lines of evidence, the IPCC was able to establish absolutely unequivocally that this increase in CO2 in the atmosphere is indeed the result of human activities. With additional methods, we can then also start to apply this to the warming that we are experiencing. On the left-hand side, you can see, again, the figure I showed, the hockey stick figure I showed before, and on the right-hand side is actually a figure that shows or that contrasts the amount of global warming that could be increased by natural drivers only, which is here in the green-blue color at the bottom, so solar and volcanic changes, and then the warming that can be explained by simulated human and natural forcing in the brown at the top. And that is then compared to the observed global warming, which is there in the very wiggly black line over time. And with this illustration, you can see that natural forcing, which we also understand quite well, can by far not explain any of the global warming that we have seen in recent decades. Also, now that we understand that CO2 increase is caused unequivocally by our human activities, we can now also attribute this warming unequivocally to human activities. Another way of looking at is in the next figure that the IPCC has included in its summary for policymakers, and where this total warming, which is shown here as this gray bar, can be split up in the different contributions. A first method to splitting this up is called attribution studies, which don't allow for a very detailed split up, but allow to split up the total warming in the contribution attributed to human greenhouse gases. This is the second red bar here, and then the cooling of other human drivers, such as aerosol or air pollution. And I think the bottom line of this figure is basically that human activities are responsible for 100% of current warming. Another more sophisticated way of looking or trying to look at the same question is through radiative forcing studies, and these provide slightly bit more detail. Here you can see again the same global bar being split up in many different contributors. What is interesting to highlight here is mainly the largest bars. The two bars on the left are for carbon dioxide and for methane, and the largest cooling bar is for sulfur dioxide, really clearly showing the importance of tackling both carbon dioxide and methane for limiting climate change, but also to keep in mind that as we will be cleaning up our skies from air pollution, the current cooling effect that these particles or these polluting particles in the atmosphere have will disappear. So we also need to take that into account when designing climate policies. And to be honest, in most cases, these are indeed being taken into account. Next statement then is that climate change is already affecting every region on Earth in multiple ways, and the changes we experience will increase with further warming. Here, the sixth assessment report was really able to do something very new that the IPCC was not able to do yet in the last assessment report that was published in 2013 and 2014. And that is really to make an inventory of the observed changes in extreme events. Here it shows the changes in hot extremes, and combine that with the confidence that we have that these changes can be attributed to human activities. So what you can see here in this graph is kind of a very it's a stylized representation of different regions of the world. I hope you can kind of see the world map in there. Every tile that is red, there we have seen an increase in observed changes. Every tile where there are 3 dots included, we have high confidence that this is due to human activities. And you can see that in pretty much all the tiles where we see an increase, there is at least medium, if not high confidence, that the changes that have been observed are part of, are caused by human activities. The same kind of overview is shown for heavy precipitation. As you can see here, there are other regions where that provide a clear trend here. So the signal is a bit more noisy here, and you can also see that the amount of agreement is much less, and that is simply because there is much more interannual variability in precipitation, so it's much harder to detect the signal from the noise. And the same is true if we look at agricultural and ecological drought. Important to see here is also that we have several regions, and I think particularly here for heavy precipitation, that is something to highlight, that are colored gray. And that really shows that there is limited data or literature in those regions. And it actually also really shows kind of an inequality in the amount of literature, science, and observations that are available in the developed compared to the developing world. So these pictures really show more than just a scientific assessment, but also show something about the capacity of certain regions to do research and understand their environment. Also beyond these general extreme events, the IPCC shows that it is likely, so that is with greater than 66% probability, that the global proportion of major category 3 to 5 tropical cyclones has increased over the last 4 decades. And that this increase cannot be explained by natural variability alone. And it also highlights that there is a strong increase in what we call compound extreme events. That is, for example, heat waves that come together with droughts, or fire weather, that is weather that is particularly subject or that is particularly favorable to producing fire in forests. And that is really found to increase also in all inhabited regions. Now, these impacts will increase further. With every increment of global warming, changes get larger at both at the regional and the local scale. Here in this figure, at the top, it shows the comparison between observed changes and simulated changes at 1 degree of global warming. Just goes to show that, or kind of shows that models are quite well at capturing these changes. And then at the bottom, you can see how the warming changes over time with per half a degree of warming. Well, for 1.5, for 2 degrees, and then on the right-hand side for 4 degrees. You can clearly see that some aspects that we know as the land-sea contrast. The land warms more than the ocean, and also that a feature which we call the polar amplification. The Arctic warms more than the global average, and that is because as the white surface or snow-covered surface melts, the darker surface absorbs more radiation, and that increases the local warming. The same kind of trends can also be found for precipitation and soil moisture. And here you can see that, particularly here on the right, there are clear regions where we will see a strong intensification of precipitation, particularly here in the monsoon regions. And then there are also regions that will be that are likely to experience much more drier conditions, the Mediterranean being a typical example of where that signal is very strong. Now, most of those are average changes. We can also look at this in terms of extremes. And here, this figure shows how hot extremes over land change with global warming, and shows the assessment of it. It shows this for a 10-year extreme event or a 50-year extreme event. And let us just look here on the right-hand side to what that tells us. It basically tells that a 50-year event that maybe our grandparents or great-grandparents would experience once in their lifetime, so from 1859 to 1900, is now already likely to occur once every 10 years. If we now increase warming to 1.5 or even 2 degrees, with 2 degrees of warming, an extreme event, a 1 in 50 years extreme event for our great-grandparents would occur around once every 4 years. And at 4 degrees of warming, that will simply be the new norm of almost every year. Just goes to show that the experience of the past at some point will become very irrelevant to what we are experiencing today and what we will be experiencing in the future. Now, I want to go to have a look at that future and look at what the IPCC says about future changes. And it has this key message here that there is no going back from some changes in the climate system, but some changes could be slowed and others could be stopped by limiting warming. And to look into the future, the IPCC Working Group 1 makes use of scenarios as tools to understand the global future. The IPCC reports are should be policy relevant, but also policy neutral. So the IPCC doesn't pick their scenarios, but has selected these 5 scenarios as a set that spans the entire literature, from the very highest emission scenario, which is labeled SSP 5 8.5, which basically involves a reversal of some of the climate policies that we see today, a recarbonization of our energy system, and thus very high emissions, to a pathway that goes to net zero, that starts reducing emissions immediately and gets to net zero CO2 emissions in the 2050s. These scenarios, they do not just describe CO2 emissions, but also all the other greenhouse gases here on the right. We show just a few, a selected few of those. Now let's have a look at what that tells us in terms of temperature outcomes. For the highest scenario, we would see warming rise over the next couple of decades and until the end of the century, well beyond 4 degrees, which was the highest level that I highlighted in the previous slides. But for the lowest two scenarios, we see that which reached zero emissions over the course of this century, we see that warming can be halted and even gradually reversed until the end of the century. In the near term, however, despite the emissions being very different, the changes between the different warming projections are not yet that clear. The changes in the absolute warming are not that different, but the changes in the rate are already incredibly important. Here, by the 2040s, for example, many scenarios are somewhere between 1.5 and 2, but some have already stopped warming and have stabilized, while others are still increasing their temperatures massively. Now, how does this reflect onto other components of the climate system? In the interest of time, I will just look here at the ocean acidification. And what you can see here is the reduction in the pH of the surface ocean corresponding to these different scenarios. And what you can see is that the change in acidification actually goes almost in lockstep with the changes in emissions and in warming. What you can see that even in the lowest scenarios, ocean acidification is gradually reversed until the end of the century. So this is one part of the Earth system that responds quite rapidly to our actions. Another aspect, however, that responds very slowly is sea level rise, which where you can see the projections here. And until the end of the century, under all scenarios, even those that halt and even slowly reverse warming, sea level rise is still continuing. There is a clear difference between the different scenarios, but all of them are still increasing. What you can also see here, and this is an important innovation of the latest IPCC report, is that we highlight there some of the low likelihood but highly impactful events that could happen. And this is this dashed line is the level of sea level rise that we would get under the highest scenario if one particular process, of which we are very uncertain but which we can't exclude, would be triggered. So if that process in which makes ice cliffs unstable would be triggered, then we would see almost a meter additional warming. So as you can see from this figure, global sea level rise doesn't stop yet in 2100, and so we can look further into the future to see where we end up. And this panel here at the bottom, which is now very hard to read, is the same panel as in the previous slide. And here on the right-hand slide, you can see now on the same scale how much sea level rise we would be getting under the second lowest and the highest scenario by the year 2300. And what you can see is that under all these scenarios, there will be more sea level rise. And sea level rise of 0.5 meter to 3 meters under a 2-degree pathway is clearly something that is still in play. For the high emission scenarios, much higher levels of sea level rise are still to be counted with, even up to 15 meters if we also take into account that highly unlikely but very impactful process of marine ice cliff instability. So finally, and I want to then stop with that, is what do we need to do to halt warming? What does the IPCC tells us there? We have now increased and very strong evidence that to limit warming, strong, rapid and sustained reductions in CO2, methane and other greenhouse gases are necessary. And this will not only reduce consequences of climate change, but also improve air quality. And here I want to show, or I want to illustrate it with this figure, which is again one from the summary for policymakers. And this figure, instead of time on the horizontal axis, it basically shows cumulative emissions. So the total amount of CO2 that we have ever emitted in the atmosphere starting from 1850. And here on the left, you can see the historical warming. And then on the right, you can again see the different scenarios now until 2050. And what this clearly shows is this very nearly linear trend between, or linear relationship between global cumulative CO2 emissions and global warming. But it also shows, and that's here at the bottom, which just shows bars of the different cumulative emissions implied by the 5 scenarios over the next 3 decades, is that the next 3 decades will really be absolutely essential in determining where we will end up in terms of global warming, be it 1.5 or already well beyond 2 degrees by the mid of the century. I want to close this presentation with a figure that is actually not from the IPCC, but instead comes from the United Nations Framework Convention on Climate Change latest NDC synthesis report. And in this, NDC stands for Nationally Determined Contribution, or the pledges that countries have put forward as part of their commitments under the Paris Agreement. And what you can see here are global greenhouse gas emissions. The yellow line is the central scenario of that was assessed in the IPCC report, AR6, that leads to 2.7 degrees of warming by the end of the century. And here the red cone, or the red triangle, is the United Nations Framework Convention's best assessment of the emissions implied by the current pledges of countries. And I just want to put this figure up as the last image of this presentation, because this really connects what the IPCC does with what needs to happen in the real world. And so this is one example of how the IPCC informs the international climate negotiations, and how also it informs what is necessary from COP26, the climate summit in November in Glasgow, in terms of delivering on strengthened and more ambitious greenhouse gas emission reduction pledges under the Paris Agreement. And with that, I thank you all for your attention, and thank you again for the invitation, and I would be very happy to answer any questions.
Thank you, Joeri. I can see a hand raised over there.
Hi, thanks for the very clear presentation. Yannick here from University of Canterbury, New Zealand. The 2-degree scenario is not a goal, right, but a place where you would like not to be. I think you illustrated that in the slide on the sea level rise, and I was wondering what your reactions on that statement is, and what other extreme consequences we see if we operate under the logic of the 2 degrees, which again is something we would be wanting to be distant from.
Yeah, thank you for that question. And I think your statement is absolutely, in my view, absolutely uncontroversial. So already under the Paris Agreement, yeah, we are not trying to reach 2 degrees. We are trying to hold warming well below 2 degrees and pursue efforts to limit it to 1.5. As part of the, there was a process in the UNFCCC that was called the 2013 to 2015 review, where policymakers took all the evidence and looked at and tried to answer what the most appropriate temperature goal would be. And as part of that process, what came out is that, and you can read that in that report, also in the UNFCCC, they say 2 degrees is not a safe limit. It's not a guardrail against which you can lean, but it's a defense line from which you want to stay as far away as possible. And I think the evidence of the report also clearly shows that. It shows it in terms of extreme events that increase. It shows it in terms of cumulative impacts or processes in the climate system that have a cumulative impact, like sea level rise, like even permafrost melt. Many of the aspects, and I didn't have time to go into it in this presentation, but the IPCC also looks at the more uncertain kind of tipping points, which can be really impactful, but are very often very uncertain, and for which we don't really exactly know or can determine when they will happen. The one thing we do know is the lower we keep warming, the lower the likelihood that they will be triggered. Some of them might be already triggered today, including permafrost melt, which is already ongoing. So I fully agree that 2 degrees is not an aspirational goal, it's not a target to hit. It is, we want to limit warming well below 2 degrees and stay as far away from 2 degrees of warming as we possibly can.
Thank you. Here, Shir, please.
Thank you very much for the presentation. This is Shir Kokish from Working Group 3. And I would just like to mention that the summary for policymakers of the Working Group 1 contribution has been very impactful and very helpful for us also to communicate the most recent findings of the IPCC to national institutions as well. One of the most impactful figures, as you also showed in the presentation, was how many more times the frequency and intensity of climate impacts will increase in any other scenario other than 1.5. And in this respect, also the interactive atlas that the IPCC presented for the first time this round, could you mention a little bit about that? And also for the impacts that are especially expected for the Mediterranean, because this part of the world where most of us are coming from, this region, is warming faster than some of the other regions of the world. So this is maybe we would like to hear more from you. And thank you very much.
Yeah, thank you for that question. And actually, I had a slide, but I ran out of time, so I'm going to share it now. So as part of the IPCC 6th assessment report, there was also one really important innovation, which I think is really valuable for anyone working in climate, be it a researcher or someone in an administration who tries to understand better what the implications are of the assessment for their specific region and their specific local situation. So the IPCC has published, and it's freely available online, an interactive atlas where you can explore different scenarios, where you can zoom into regions. You can not only look at kind of the temperature assessment, but also at the assessment of the various literature that is available for what is happening and what is projected to happen in a particular region. So here you could look into the Mediterranean and really draw out all the evidence that is available. So I can warmly recommend anyone to that is interested to go to that website and to check this out. It has already been highly successful and highly popular. So and we are very happy that it is, of course. And I don't want to go too much detail because it would just lead us too far. But indeed, there are very important regional differences in the climate signal that we will be seeing. And very importantly, the Mediterranean region is one of those regions where we see a very clear signal of drying. And that is interesting because in a warmer atmosphere, actually, we would expect, we know from basic physics, a warmer atmosphere can contain more water vapor. And what goes in the atmosphere also comes down, so you would expect that you wouldn't see that much drying, but that water or that precipitation really comes down in a very unequal way, with some regions experiencing much more intense periods of precipitation, while others actually still drying, and the Mediterranean is one of those regions.
Question here and then there.
Hello, thanks for the nice presentation. I am Eugenio Molina from Alcalá University in Spain. My question is, well, those infographics were great, but I was wondering why 1850-1900 was chosen as a baseline period, because it's kind of far away and difficult for us to relate the changes to that period. Thank you very much.
Yeah, so that choice is actually 1850 to 1900 is taken as a proxy for pre-industrial conditions. And the reason why we relate it back to pre-industrial conditions is that the international climate targets, the 1.5 degrees of warming, 2 degrees of warming, and every time there is a level mentioned, this is relative to pre-industrial conditions. Of course, the Industrial Revolution started in 1750, but until 1850, we have actually observational records, and so our estimate of the warming since 1850-1900 is the most accurate one. If you go further in time, there might be still like a tenth of a degree difference until 1750, but ultimately that is kind of relatively minor compared to the warming that we are experiencing today. In terms of why do we express changes in extremes compared to 1850-1900, well, it's the same reason. So we can link them to particular warming levels. If you would express them relative to, for example, 1950-2000, then it would be harder for us to link them to, than for example, the increase in extreme events would be relative to that period. The global warming would be expressed to a different period. And so ultimately, we thought that would be more confusing than helpful. Of course, one can always do the calculations oneself. Unfortunately, that's not part of what we have in the report.
My name is Luís Serrano. I come from Portugal, and I want to thanks for your impressive work and for this very interesting presentation. And I have two questions. The first one is that about the relation between carbon and oxygen. You said that it correlates well with the combustion, but what about deforestation? What is the contribution about deforestation that we felt in the globe in the last century? It also, I think it will have an impact on that relation, but what could be the real impact of that? And also about that interesting graphic showing us that we have CO2 contribution and methane also. But I was very surprised about the importance and the relevance about the methane. And we all talk about CO2, but we saw that methane also plays an important role in that global warming. So what do you think also about that? Thank you.
Yeah, so to get Thank you for those questions. So your first question, indeed, it's fossil fuels and deforestation. Deforestation currently, annual emissions, roughly a tenth of fossil fuel emissions. So it's not negligible, yet it's clearly an order of magnitude smaller than what fossil fuels are currently causing. But equally an important aspect to be dealt with, in particular because restoration of ecosystems can actually help to also increase the resilience of those systems in taking up carbon. Part of our carbon that we put in the atmosphere is indeed taken up by the land and the ocean carbon sinks. Your second question was on, wait, can someone remind me?
Is methane,
yes.
Methane contribution?
Yes, so the methane contribution is indeed important, and the big difference between methane and CO2 is that CO2, basically, some of the CO2 that we put in the atmosphere is forever. We put it in the atmosphere, some of it gets redistributed in the ocean, some is in the land, some stays in the atmosphere for tens of thousands of years, and this is basically forever on human time scales. Methane is very different. It warms a lot, but it has an atmospheric lifetime of, let's say, of a decade. So that means if we reduce emissions, if we reduce methane emissions, the concentrations will quite quickly decrease, and the warming of methane will disappear. Whereas if we bring CO2 emissions to zero, the warming of CO2 won't disappear, it will merely stabilize. So we won't add any more to the warming, but we also won't, it won't disappear. And that is the big difference with methane. Both are very important, and both are parts of an integrated approach to limiting warming to as deep levels as possible.
Okay, do we have questions from the chat?
Yes, we have one question.
Yes, there was one question that I saw on the issue on permafrost, and I'm happy to respond to that. Yes, the permafrost is an important component of the Earth system. So the question is whether, what do we do about the assessment of permafrost, and whether there is evidence for kind of methane bombs or something, quote unquote, methane bombs. Well, our assessment is that the permafrost will definitely contribute and is already contributing, but there is very little evidence that there would be these kind of sudden releases of methane that would happen at the global scale. So what we see there is a very important distinction between what can happen at the very local scale, in a single lake, in a very particular geography, and what can happen across the entire Arctic, across all the permafrost of the Arctic, in order to have a global impact. So in permafrost we can see localized abrupt changes, but our best assessment is still that this would provide, or this will result in a steady contribution of additional methane and CO2 emissions to the atmosphere, which ultimately will further exacerbate with global warming, or with our human contribution also increasing. So the warmer we make it, actually the harder it will be to stabilize warming thereafter, and potentially we will be needing even carbon dioxide removal at the global scale simply to stabilize global warming if we let temperature rise too high in the first place.
Okay, thank you, Dr. Rogelj. And before closing the session, I just want to reflect on your last slide. We've seen that even though with many strong messages coming out of IPCC fifth assessment report, we didn't manage to persuade the world to deliver on 2-degree or 1.5-degree pathways. So what is your opinion? Are you optimistic that with the new findings of assessment report number 6, the science will be able to persuade the policymakers to go for a better climate future of the Earth?
Yes, good question. Thank you for this one. Well, I think I'm always optimistic, and I'm also realistic. I know that science in itself doesn't persuade anyone, because we are not always rational beings, and it's not because we have all the evidence that we make the right decisions. And I think with climate change, it is the same. But I'm optimistic in a way. I mean, let's start this by saying that the best time to have started climate action was 3 decades ago. And we should have started, and a decade ago was also better. But now we are where we are today, and there is still a lot that we can avoid in terms of climate impact. And I think the big difference is that the science is established, and Working Group 1 once again, now there is really no doubt, there is no doubt that it is happening, that we are responsible for the many changes that we are seeing. But I think the most important change in the story or in the context is what Working Group 3, so the Working Group on Solutions and on Climate Change Mitigation, will provide us. And there is really a total shift happening in the energy economy, in our societal context. And even if that is still not going fast enough at this stage, that makes me optimistic that together with the knowledge and the evidence that we have to do something about it, we now also have the options and in many cases also the imagination of where we want to go. And one can see it with many countries putting net zero targets these years, or in the past couple of years. Of course, these are just targets. Now we need plans to implement them. But I think that is a really important aspect where countries as a whole, the businesses in those countries, the civil society understands that just reducing emissions is not enough. It is really to stop adding CO2 to the atmosphere, to stop using the atmosphere as a free waste dump for combustion gases, is basically where this needs to be heading. And there I'm optimistic. I'm pretty sure that the climate summit in Glasgow won't solve it all, but I'm optimistic to see good progress there, both on mitigation and on delivery on finance, the 100 billion or more that is needed to support developing countries in their adaptation and mitigation efforts to make this transition together.
Thank you, Dr. Rogelj. Please join me in applauding Dr. Rogelj for this excellent presentation. Thank you also everybody for the contributions, and now it's lunch break. Thank you.
Thank you. Bye-bye.